Hello and welcome back to my distributed training series. Today we'll talk about torch.distributed package. So here's the series progress so far. So first we've discussed data as model parallel. Just two of the many parallelism approaches, and we've discussed that data parallel is the simplest, that did not require any changes to the model code. You can just plug in a simple wrapper and it will work. We've discussed a wrapper that can do that, torch data parallel, that does not require multiprocessing, that you just plug into your code and you can use it, but it will only work on one node, so one node multi-GPU setup. And second problem is that due to global interpreter lock in Python, it will actually be quite slow in extreme cases. So today we'll discuss torch distributed, which is basically a cross-process communication package. And we'll see how it basically solves both of these problems. So it will allow you to be faster because have multiple processes that do not require locks between them, and you can scale your training up to multiple nodes as well. And here is the plan for today. So first we'll discuss what is torch distributed and where it's used. Then we'll just basically look through a simple script of how to get started with torch distributed, and we'll discuss several launch options to actually launch your multiple process. So one of those will be just local launch by hand, the simplest one, yet it allows you to see what is actually happening. Then we'll discuss torch run, slurm, and we'll also mention some other ways you can set that up. Then we'll write a little bit of code to do peer-to-peer communication and collective communication with torch distributed. And finally, we'll look at how we can actually debug these distributed applications. Okay, so what is torch distributed? Remember when we talked about data parallel, we've discussed that when we do data parallel training, we don't really need to change the model code, and then forward and backwards path actually happen on just one device. But eventually, to do the gradient descent step, you will need to do this cross communication, where you actually exchange gradients between the devices. So torch distributed is a communication package that allows you to do just that. So here is the tutorial about torch distributed from PyTorch itself. And it all basically starts with just initialization of a process group, which is basically, let's say you want 16 devices spread across two nodes. What you will need to do is launch 16 processes on those 8 on each of the nodes, and then let them know that they are supposed to work together. So it usually happens by providing some sort of environment variables like master address, master port, and also the rank and the size. So rank is your current number, which will pass into every process, and size is the total size of the world, which is 16 in our case. So you'd usually see that these setups use localhost or this IP address, but it's actually not limited to that. So as we'll see in a bit, when you launch with Slurm, for example, you can provide any network address for the nodes to communicate with each other. So this thing will also work for multi-node setup. It will also work for high-scale LLM training with hundreds of nodes. So it's really quite powerful. So what is torch distributed? In short terms, it's a communication package. So when you need to exchange gradients, when you need to exchange information between devices, you would need to send information over the network or in other ways to communicate between your devices. So here is a PyTorch tutorial page about different communication backends. So the one that is usually used for GPU training is called NCCL, or Nickel as it's sometimes called, and the N stands here for NVIDIA. So NVIDIA basically wrote their own low-level communication package that deals with a lot of complexity involving GPU training. For example, if you need to send tensors from one GPU to another, you don't want to copy the data to a CPU, you don't want to involve system calls, you want it to be fast, you want it to be effective, and NCCL does that. So it allows you to copy tensors directly from one GPU to another. And if you actually think about major breakthroughs in training in recent years, like with NVIDIA H100 GPUs, one of the core things NVIDIA actually did was implement these high-end, high-throughput communication capabilities into their GPUs. And I'll just sort of show an example blog that I've read about this. I'm not going to dive into too many details. I'll just leave the link in the description, where a guy talks about an example instance from Amazon Cloud that actually performs such training. So this is called P5 instance from Amazon with 8 NVIDIA H100 GPUs. And the speed for that is 3,200 gigabytes per second. So it's not 1 gigabyte, it's 3,000 gigabytes. That's like, what, 10 GTA 5 game downloads per second. So it's insanely high speed. And that sort of communication speed requires quite a lot of effort on the software stack as well. So you don't want to use TCP/IP because it had a lot of trade-offs from the start, that like timeouts and stuff that does not work anymore when you have really high speed, really low latency. You don't want to use network. You don't want to copy stuff to CPU. And so this blog post talks about stuff like RDMA and libfabric, which are basically low-level libraries that allow you to make your network communication faster in these cases. So all of that is hidden from you. So it's part of that is hidden in NCCL, Nickel, or other backends that you might want to use. And all of that is wrapped around in torch.distributed package. So you will not have to write low-level network communication code or CUDA code. All of that is already done for you in torch.distributed. And torch.distributed is the package that is used for most of the distributed training nowadays. So you can use it just in your own code. It will be used in libraries like Huggingface Trainer, PyTorch Lightning, Nemo from NVIDIA, Composer. All of them will have torch.distributed as the low-level communication layer. Okay, so now let's actually launch some example processes and see how they communicate. So here's my code, which is pretty much the copy of what we've just seen on official torch.distributed tutorial. So for now, I'm just doing setup. So I'm going to launch a couple of processes and let them communicate with each other. So to initialize this communication, we need to call this dist init process group, which basically allows them to connect to each other, to make them aware of each other. And in the end, it will unlock some of the torch-distributed calls for you, like get current rank, get world size, send a tensor somewhere, receive a tensor, perform collective communications like all reduce, and so on. So here I'm also using these environment variables, and I'm also going to pass in world size and rank in environment variables as well. So this code is single process Python, so I'm not starting any threads, any sub-processes here. It's just a script that I'm now going to launch from a command line. And we can see that it's going to print some stuff before and after the initialization. And let's just see what happens. So let me go to my terminal, and I'm going to start this code with this option. So I'm going to use world size of 2 and rank 0. So this is going to launch one process, and it's going to tell it that expected world size is actually 2. So when I do that, I can see that it will print some stuff before the initialization. And it says that, okay, here's my master address, it's master port, it started initialization, and the current rank is 0. And then it just patiently waits. So why does it wait? Because we just told it that the expected world size is 2, but I've just launched one process. So it's going to hang in there until some sort of timeout is reached, like 5 minutes. So it's just going to basically wait for other processes to connect. So let me spawn a second process. I'm switching to another tab. and in that tab I'm going to launch the same script but with rank 1. So let me do that. So this one was quite fast, so it also printed all the same stuff, and it says starting initialization of process group, but now current rank is 1, and it just instantly finished the initialization, ran a function that I did, and just exited. And if I switch back to my original tab with the rank 0, it also proceeded. So it was waiting for the second process to connect, and then just as soon as the second process connected, it just prints everything that I asked it to and just exits. So here's the example script, which is not really doing any communication apart from the initial setup. And for now, I've just launched the processes by hand, and I let them communicate across localhost. So just single node, many devices setup. Let me now show you how you can do the same with Slurm and many nodes. So first of all, what is Slurm? Slurm is basically a cluster setup communication library that allows you to ask the cluster for several nodes. It allows you to launch a script on several nodes at once. So it basically simplifies this setup of having to manually start several processes. It basically does that for you. So I have a cluster at my disposal. I can see that I have 3 idle nodes. Okay, 2 will be enough for me. So I have this run script, which now says that I'm going to provide a proper master address as some sort of a host name that belongs to one of the nodes that were allocated to me. And I'm also going to ask the Slurm cluster for the number of tasks that are currently being launched within this job, and for my current rank. So basically this part is transferring the knowledge about what is the world size, what is your current rank, what is the master that I need to connect to communicate from Slurm to my script, and then launches the same main.py. And so here is how I can launch it. So I use the program called srun, which is another command from Slurm, which says that I'm going to just launch this run.sh script that we've just seen, and I'm going to do that on 2 nodes with 2 tasks. So let's see what happens. So I can see that they both launched. Slurm copied the standard output and standard error to my current node. But I can see that now master address is this remote node somewhere on my Slurm cluster. I can see that both of them have started, connected to each other, and finished. One with rank 0, one with rank 1. So basically, this torch.distributed package allows you to set up cross-node communication as well. So this also means that any tools that you've seen being used for single node setup and multi-GPU that use torch.distributed underneath, they will most likely also work for multi-node training. And that includes Huggingface Trainer, Torch Lightning, Nemo, all of that. So let's discuss what ways to launch many processes there are. So anytime you want to do distributed training, you will need to launch many processes. And the simplest way to do that is just to manually do that n times, which is not really what you want to do if you have hundreds of devices, because every time you want to stop and restart the training, you'd have to do the same thing of calling a script 100 times, which is quite laborious. So that's not what you want to do usually, but it's nice to be able to do that and just see exactly what is going on there. Another popular way to just start multiple processes on a single node is called torch run. You might have seen that in tutorials, you might have seen that in model explanations, which basically spawns several processes on the same node and also passes in those required environment variables like world size, rank, and so on. And we'll see how it works in a bit. Another popular thing is Python multiprocessing, and this is actually what will happen under the hood in libraries like Huggingface Trainer and PyTorch Lightning, where you think that you start just one Python script, but it will automatically discover that you have many GPUs on your node. It will spawn more processes with Python multiprocessing or forking or otherwise, and each of those processes will connect to its own GPU, and they will all communicate using this torch.distributed package. I tell that now because it might not be obvious what is happening, because it sort of happens under the hood, but it's nice to know that this is what actually happens. Finally, there are basically cluster libraries that were specifically created for that, and that includes Slurm. Another popular one is MPI, and this is where basically you now have access to many nodes, and you just log into the head node and you ask the cluster to provide you with some resources, and you just say that you need to launch this script on n nodes and k processes per node, and then the communication package deals with everything else for you. So now let's try to do the same with torch run. So I have this command now, so torch run, which is going to spawn several processes on my one node, and it will going to spawn 2 processes per node. And I'm going to use the same main.py script without any modifications. And I can see that it auto-discovered some sort of IP address. It also spawned 2 processes just as asked, and it said that for one of them current rank was 0, for another one current rank was 1. So all it does is basically spawn multiple processes on a single node. And I can ask for more, just to demonstrate that all the same setup will work for more devices. So here we've spawned 4 of them, all of them got connected to each other. We have ranks 0, 1, 2, 3, all of that will work. Okay, now let's discuss how to actually send data, and we start with the simplest example of just peer-to-peer communications. So here is the modified script. So all the setup is the same. So I'm going to spawn several processes externally. I'm passing in all the required environment variables to actually initialize the process group. And I have this function called rank that actually performs some stuff. And so in my case, what I'm going to do is I'm going to spawn a tensor of zeros, just 1 0. And then depending on what is the current rank, I'm going to do different stuff. So if the rank is 0, I'm going to increment the tensor and then send it to rank 1, and then increase the my local version of the tensor by 2. And let me just jump back to terminal and launch it with torch run. So I'm doing that for 2 processes within one node. And we can see that, again, both of them started, both of them connected to each other. It is quite hard to understand what is going on because they do everything in parallel, and the prints that they do basically merge with each other. We'll fix that in a second, but you can see that one of them got the tensor of 3 as we expected, and another one got the tensor of 1. So basically, the rank 0 got the tensor of 3 because it incremented this tensor here, and another one just received the tensor, which has the number 1 in it. I can now slightly modify the code to use more devices. So now I'm saying that rank 0 is going to increment the tensor, send it, and then increment again by 2. Rank 1 is going to receive this tensor, and then rank 2 or any other rank is not going to do anything. And I'm launching it like this. So I'm going to do torch run with 3 processes, and let's just see what it types. So now I got 3 processes initialized. Rank 2 has tensor with a 0 inside because it's not receiving anything, because we've just said that only rank 1 is going to receive this tensor. And then rank 0 has I guess 3, and rank 1 has a 1. But it's a bit unclear because the output got merged together, but it's not a big problem. Now let's discuss collective communications. So we've just seen point-to-point communication where we basically have a world and we just say who sends what to who. And in reality, this is only going to be needed if you actually implement some of the niche rare algorithms yourself. In majority of distributed training, you don't really need to do that by hand, because what you need to do usually is just to perform something like all reduce or all gather across all the devices that you have. So, for example, in data parallel approach, what you need to do once you have gradients version on each of the devices, you want to sum that up across all your devices. And it's actually not that simple, because if you want to do it really fast, you can have several algorithms on how to do that. So you might want, if you have several nodes and several GPUs on each node, you might want to exchange gradients across GPUs on one node first, because it's faster, and then send one resulting version to different nodes, and so on and so forth. There are different algorithms on how to do that effectively. And thankfully, we are just using torch.distributed package that already has all of that built in. So what it will do is actually understand what sort of cluster setup you have, which GPUs are located on the same node, and it will decide on the most efficient communication strategy for you. And what you will need to do is to just say what you want. So do you want to reduce? Do you want to do anything else? And so on. So let me show you an example of all reduce. So all reduce, what it does is basically perform some sort of binary operation across your tensor for every device that you have. And that might be every device in the world. So if you have a world of size 2, it will perform it for 2 devices. You might also specialize it further. You might create your own group, which is like a subgroup of the entire world, and perform this reduce for your current group only. And so what all reduce is doing is it applies this operation, which in my case is just sum. Basically, before this operation, we had a single tensor on my current device. And after this operation, this same tensor is going to have the sum of this tensor version across all the devices. So let me launch that. So I'm going to use 3 processes per node and just see what happens. So I've launched 3 processes, but remember that I've actually doing this all reduce only for my group with 0 and 1 rank. So what I can see here is that for the devices that are in that group, so the device with rank 0 and 1, the sum is going to be equal to 2. And then for the device that is not in that group, the sum is going to be 1, right? We can remove this part about the group. In this case, the all reduce is just going to perform this reduce across the entire world. So I do the same now, and I expect to see a 3 in every of that, right? So this one has 3, this one has 3, this one has 3. And on this page, the distributed torch tutorial, there are different functions that you can use. So all reduce is basically performing any binary operation to turn several versions of the tensor in just one version. So it can be a sum of all tensors, it could be a product, max, mean, or anything else you define which turns 2 numbers into 1. So anything like a plus b, or a multiplied by b, or a custom operator, you can ask torch.distributed to apply that custom operator to all the elements between devices. Apart from that, there are other operations like gather or all gather that just sends copies the tensor to different device, broadcast, which takes the tensor from one device and broadcasts to other devices, and so on and so forth. So from my perspective, the all reduce one is the only one we will need for data parallel. Sometimes we'll also see gather or all gather used in code as well. Finally, let's talk about distributed debugging. So first thing you can do for debugging distributed code is just to try and do that in VS Code or Cursor. So I have my launch.json file, which basically says to run this torch distributed run module with 2 nodes. So what will happen when I press this debug button is that it will launch this torch distributed module that will in turn spawn 2 processes, and my debugger will attach to both of them. And I'm asking it to break before this all reuse operation. So this will sort of work, but it's a bit inconvenient because you'll have 2 debuggers running at once, and if you have 8 processes, you'll have 8 debuggers running at once. So it will basically mess your execution process because the debugger will jump back and forth. So I can ask it to print the current rank, for example, and it will say that it's currently connected to rank number 1. I can print the content of the tensor before the reduce, and then if I say that I want to step over, well, now it's basically jumped to another process instead of just stepping over to the next line. So it's a bit inconvenient. I can still sort of see what's going on. So after 2 presses of this button, I've switched to the next line, and I can see that now the tensor is reduced, so it got summed up over both of our devices, and I'm currently on rank number 0 still. So it sort of works, but it's not ideal because of this jumping around between processes. The second thing we can do is the torch distributed breakpoint. So to use it, I simply say put the breakpoint in code like this, similar to how I would do that with PDB or IPDB, which are famous debugging packages for Python. So I insert this line here, which says that I want to put a breakpoint in the code, and I want to connect only to rank 0 on this process. So good thing about this is that now it will launch in the terminal no matter how I spawn the processes, and so it will work with slurm and srun, for example. So this srun command can be made interactive like this. And so what will happen now is that I spawn some process from my head node. The slurm will connect me to these processes, and only on one of them will the debugger connect to the actual code. And in other processes, it will just patiently wait. So it basically inserts an extra barrier to make sure that the processes do not trail off, they do not time out while waiting for you to decide what to do with the debugger. So I'm here before the tensor reduce, and now I can print out everything. I can print my current rank as well. I can step over, and now I'm still on the same rank. So thanks to this torch distributed breakpoint, I'm now connected only to the first rank with ID 0. And that is easier to navigate because now you just use it as your typical debugger. And so I can print the tensor after this reduce operation. Sorry, that was before, and now after. Okay, now it is 2. So this is now a bit different, right? So I am now connected to one process, and I debug it as if I'm connected to one process. But at the same time as I'm stepping through the line, all the other processes are still running and still waiting for communication. So I'm connected to one process, but all the other processes are still there. They're doing their part. They are exchanging information with me. So this is basically the 2 tools you might need to do distributed debugging. So the first tool, just debugging in VS Code, is useful because you can actually connect right there in your IDE. You might also just debug a single process. if you just want to experiment with model code, for example. So one thing that will not help you with is debugging the actual communication operations, because it's not really interesting to communicate when you just have one process. And for that, you might switch to torch distributed breakpoint. So this was it regarding just the introduction and overview of torch distributed package. In my next video, I want to actually use it to train a simple neural network and see how it works. And in addition to that, we'll see how torch distributed data parallel wrapper works and how to implement that yourself. Thank you for your attention and see you next time.